Oh, thank you. Yeah, sorry, it cut out there just a little bit at the end. I think you handed it off to me if I'm right?
Yeah.
Okay, awesome. Yeah. So, hello everyone. Thank you for joining me on this session. Is we're going to be talking about specifically relational databases and a resurgence as of late that we probably noticed. But first things first, just a little introduction to myself. Thank you very much for that the paragraph of introduction. I say fortunately for the world, as far as kind of ugly websites and since evolved really just for the sake of the world, not because I write spectacular code or anything like that. I am indeed the world's okayest developer. And I work on the developer relations team at MariaDB. So basically, I try to enable really good developers to do really awesome things. And then I try to just help facilitate that. If after this session, you have any questions for me, feel free to hit me up at robh@mariadb.com. You can follow me on Twitter. You can even judge some of my code on GitHub. That is good for a laugh, especially on a Friday if you're looking for a good time. But today we're going to be talking about databases. And I like to make things simple, starting off so that we can kind of build up and get everybody running at the same pace. But as we think about databases, we think about essentially just data, right, that we can stick in this. I've got kind of this image here of something that forms some kind of bucket or some area you store that data in. And the idea is that you persist it. And that's simple enough, but how did that become so much more, right? Over the years, we've seen terms like NoSQL, SQL, NewSQL, any kind of SQL we can think of, right? Relational databases, spatial databases, non-relational databases, and the list really goes on as far as how you can be able to maybe store and even access data and what all that means, right? So we're going to take a look at that, and essentially as we dive into relational databases and really that resurgence that we're seeing recently. But first, we need to take a step back in time and take a brief look at the history of databases. Well, when I say that, right, and I kind of describe the definition of data and being able to persistently store data, certainly we've been able to do that before this timeline, right? So as you look at kind of starting at the 1960s, well, I mean, we've been able to store data in a variety of different ways. We've been hammering on stone tablets, we can write it on scrolls, and there's even these very ancient things called books that we used to use that we can store data in as well. But what we're specifically going to take a look at is, this idea of the computer era, right? This modern computational way or digital way of being able to store and persist data. And that really, the story kind of starts in the 60s and really centers around IBM, small little company you might have heard of. Well, apparently they are a very big deal, especially in terms of the database history. And we're going to dive a little bit into that. In early databases, right? So as we kind of take a look at the very beginning, in the 1960s, it was all kinds of experimentation going on with persistent data storage. And this was largely led by Charles Bachman and a group that he had at IBM that were really chartered with this idea of being able to store and persist data and then be able to access it for what would be the modern developer at that time. And so they pumped out a couple of models, right? These, you can think of them as processes or systems or organizational techniques for being able to both store and then access the data for whatever you want to use it on. And there were a couple of models, the network model and the hierarchical model. We're not going to dive too much into what these are, other than you can kind of get the gist of a network, that makes sense. We have an idea, and then you look on the right-hand side, a tree. But what you may not know about these is that they were nasty to implement. They were, hard to maintain, and even harder, really, and more confusing, really, to access the data in a way that developers could focus or keep the focus on whatever solution they were trying to create. Very similar to today. Instead of having to always get in and constantly maintain and work with the database. And so that's what really introduced the relational era, right? This idea of being able to use relationships, which we'll get into. Well, that was kicked off by a guy named Edgar Codd. So E.G. Codd also worked for IBM in 1970s, wrote a paper. And really the idea was to create a simpler way of being able to store and access data. And So he wrote this paper, which then kind of sparked this movement of the relational system or modern relational system as we know it today. And just for a quick refresher, what that means is that in its simplest terms, we've got a collection of rows and columns which form a table. In that table, then you have data types, right? The ability to specify, you've got an integer, a varchar, a string, you've got a bit or a Boolean value, something like that, where you're actually getting to specify not only where the data lives inside of this table, but what it actually consists of or what you can expect. And then of course comes in the other part where these tables or entities you can think of, you've got more of them, and you want to be able to relate them, right? Create relationships between the different entities, storing something in a tabular manner that you can connect to a different table, data that's stored in a tabular manner. And this is for a couple of reasons, right? As I mentioned before, EG-COD and IBM were really looking to simplify the ability not only to store the data, but how you actually go in and retrieve it and use it for real applications. And in turn, if you think about the 70s and the kind of limited resources that they had at the time for modern computers or computational engines, they really need to eliminate redundancy to make things super efficient so that it would work really well. And the relational model lended itself to this, as opposed to other data models that we've seen at that time really well. And ultimately, it was all around this idea of being able to improve integrity, being able to know what the data was, or what the data is supposed to be, and knowing exactly where it is. This all comes together to be able to very efficiently and very quickly be able to get up and running and use a database within your system. And this became so popular that in, throughout the mid 70s into the mid 80s, around 1986 actually is when it became a standard, but this language, right, used to manipulate all kinds of things, specifically targeted at the time at relational databases, and it's called the structured query language. And the American National Science Standards Institute and the Standards Institute for the World basically said, hey, we're going to get behind this, and this is essentially what we want to use as a language. Well, this was really kind of kicked off and really developed by a couple of other IBMers. So we're starting to see a trend here where IBM is really heavily involved in Don Chamberlain and Ray Boyce really kind of kicking that off. And they came up with this idea of this standard declarative language, and we'll dive a little bit more on that in the next slide, but this declarative language that defines a couple of different things, as you can see here. Now, some of these came a little bit later, but as you move from the left, where you've got the data definition language, you've got data querying language, data manipulation for DML, the control language, and for transactions that eventually came. And we don't have to dive too much into these, but this is everything from being able to create some kind of construct or entity to be able to store data into, to being able to, of course, query it, to manipulate the data, inserts, updates. Eventually, you got this idea of being able to control access to particular data, and then this whole idea of transactions, right? Being able to create atomic type app operations that either are going to happen or not going to happen, and be able to have that consistency and reliability so that whenever you build something, it maybe possibly not out of date or the wrong type or something like that. And for a refresher for SQL statements, what this looks like in a practical standpoint is you can think of the ability to create, again, this entity or this table, right? You've got a definition here. So create table, and this new table called task with a couple of different fields, ID, description. You're, of course, adding, different parts and descriptions about those fields and how you want to store that. Not necessarily so relevant, but that creates the entity. And then, being able then to use the DML or, the manipulation portion to actually insert information into that entity. And then, of course, the whole idea is that, you want to create an application or some kind of solution where you can read that from, right? Some kind of querying language. But as you can see, as you kind of dive a little bit deeper into what these statements are saying, there's nothing about these statements that are saying specifically, go to the, spot on disk and store, this information for the task table. In fact, you don't have to worry about that. And that's where the declarative nature of SQL comes in, where essentially you're just focused on the end result, being able to create a table, being able to insert data into the database, or being able to select data. The actual parts and the bits underneath the hood, we'll get into a little bit more as we talk about database management systems and the implementation of SQL. and why it being declarative is so important. But that's the gist of it, right? And so SQL has taken off, and it's fire at this point. As the kids say, and I'm sure kids back then said it too. Like, this is fire. Structured query language is awesome. We're going to build everything on this. And in fact, that's pretty much what happened for a couple of decades, right? Some of these smaller companies you may have heard of, Oracle, SQL Server, and MySQL, kind of cropped up in the 80s. Of course, some of these companies existed before, but their database systems cropped up really in the 80s and 90s and started to gain a lot of popularity, right? Really starting to create applications and different types of solutions using a relational database. Well, this was facilitated in large part by something called the Database Management System. You may have heard of it, DBMS or RDBMS. And what this means is that, as I spoke about SQL before, and really the relational database, is that being able to connect those things in some kind of standardized or consistent way that users can use reliably involves being able to create some kind of management system. And this added a bunch of parts, right? It added things like security or authorization, authentication, the ability to handle multiple sessions, right? So if you've got an app or you've got individual users using a client to be able to connect to it. And then you've got the implementation of SQL themselves, which can vary slightly, right? As you think about the structured query language as a standard, the implementation may be a little bit different for Oracle as it will be for Microsoft SQL Server or MySQL. But this idea of the database management system is what facilitated what we now know as, in large part, modern application development. So much so that what started as smaller transactional or operational applications where you're wanting to save CRUD information, or you're wanting to build an application to store some kind of data. Well, that, as we know, can start small, right? As you're solving the problem, and then as time goes on, you may accumulate more data, or as the application becomes more complex, you may be taking in more data, or maybe even you're pretty popular and you've got quite a bit of users. All of these things happened at once. And so over time, specifically in the mid 90s into the early 2000s, what happened is that data exploded, right? And as you see here from bottom to top, we moved from more transactional, right? Where we're specifically just trying to work on the CRUD information or operationally sticking data inside of the database with our applications, to being able to have analytical usages of that. And that's because over time, right, over usage, we have massive amounts of data itself that we can start to use to help us, facilitate the application, or maybe, help guide user input or the way they may use the application based on past behavior. Right? A lot of the things that we're seeing now within the data world. And well, at that time, really primarily in the kind of mid 90s, early 2000s, we started to experiment around of how we are going to fix our issue of things like decreased throughput. So as we got more data inside of our monolithic relational databases, we needed that increased throughput, and we really needed to have decreased latency. Basically, the golden ticket for creating a very snappy, popular application, right, that users are accepting as their expectations grow and grow. So we did what anybody would do, was we maxed out this monolith, these machines. We just bought a bigger, beefier machine. And this idea of being able to just buy a bigger box or more resources is known as scaling vertically, right? Being able to allow more space, basically more memory to be able to have available to your database system so that it can do that. Well, these machines cost more money, and it's kind of an endless process, right? Data is just going to keep growing and growing. And so this isn't a very, I guess, resilient or maybe flexible way in the future of being able to maintain that scalability or handle that scalability. And so took a look at a different approach. Well, what if we bought a bunch of medium-sized machines or small machines or something like that? Instead of scaling vertically, we decided that we would just add another machine, and then we could start to push the code into maybe more application logic to say, hey, if there's this data, it goes on this machine on the left, or this database on the left. If there's this data, it goes on the machine on the right. And I mean, that sounds like a pretty good idea, right? We can just scale horizontally. Well, this whole idea of partitioning, or what became known as sharding, unfortunately, just isn't isn't something that is easily maintained, right? It ends up being very complex and it pushes what normally would have been in the database layer into the application layer. And so more your burden is on the database administrators, application developers, maybe some sysadmins, in order to help facilitate these things outside of the database management system. So it ends up being a very complex and ultimately brittle way of solving the problem. And we limped along for a while until 2009, 2011 time period. We saw some papers come out on this idea of a non-relational database or a NoSQL database. And this was this NoSQL revolution that really kicked off in that 2009, 2000 time period. And what the easiest way, if you're not familiar with NoSQL, and if you are, I hate to disappoint, we're not going to dive deep into it, but if you're not necessarily so familiar with it, the key takeaway here is that very similar to the 1960s, where IBM was really experimenting around with different types of data models that just weren't very useful or very feasible at the time based on the different resources that were available, different hardware that was available. Now, in 2000, or at least jumping back to 2010, a lot of this stuff was very feasible, right? We didn't necessarily need to worry about the horsepower of a machine or memory or storage of these things that existed or didn't exist back in the 70s. And so we could take another look at this idea of using different types of data models as opposed to the relational model in order to be able to both store and access data. And this is awesome because these types of data models were great, right? You talk about document, key value, graph, column value. And a lot of these things, which I'll get into, we can relate to modern database systems that exist today. But their charter was to try to solve a variety of different problems that they were hitting. Now, I mentioned this idea of scalability, but there were several other problems at the time that we were starting to see within modern application development that relational databases just weren't great at handling. You know, scalability was one thing, but this ability to create more flexible data, right? So you didn't have to get in there and do a schema update, you know, to tables or collection of tables every single time, and then have to worry about versioning, you know, as mobile development and IoT became more and more popular. This idea of data availability, solving, you know, being able to have data that's available, not just necessarily within your locale, but maybe across the world. And a big one was performance, being able to use very specific data models, right? As we saw, document, key value, to do very specific things, right? If you think about caching, or you think about being able to, you know, pull a document that you're not necessarily concerned about relationships necessarily, having to build all these relationships, just pull the document as a whole. It can be very efficient and very quick. And that's the whole point, right? So the NoSQL purpose, right? Its real mantra is that if you think about, you know, all these people pushing an object, you can think about NoSQL as this person out in front. And this object, right, is a sphere shape. And a sphere you can think of as being very good at a couple of things, extremely good at it, right? You can push it, for instance. It's very good at being pushed. But the downside of that is it's not very good at holding up against a strong wind, right? Because the whole idea is that it can move. So it's not going to sit there and remain stagnant if you needed to hold up against the wind. And if you wanted to stack different balls on top of it, it's not really that great either. On the other hand, some of the more older school relational systems, one of the reasons why they were so popular and so versatile, even now, before we get into more modern, you know, innovations, is that they're extremely general purpose, right? They can do a lot of things, and they don't necessarily do everything, you know, the best, but they do almost everything extremely well. And things like, for instance, you can push it. It's not the best at it. You could certainly have it hold up against a strong gust of wind. And then you could certainly stack things on top of it, right? So it creates this idea of more general purpose use case. And that's important because at the time, NoSQL was really seen as the answer, right? The silver bullet that was going to solve all of our data problems. But unfortunately, some of the things that we realize is that we still needed transactional support. We still need this idea of asset compliance and this atomic operation and consistency, immediate consistency, to be something that we needed within our, you know, real operational systems, you know, systems of record, being able to create actual applications in the enterprise world that we could rely on. And so this left the door open in a good way, right? It turned what was the NoSQL revolution into this idea of the data revolution, right? Being able to have a variety of different database options to solve a variety of different problems. And we've got a spattering of NoSQL and NewSQL and regular SQL and all kinds of different database management systems on here that can solve all kinds of different problems. And one of the really cool things about this whole data revolution is finally getting into this idea of the relational resurgence, right? Relational databases throughout that decade, right, 2010 until now, just didn't sit back and say, oh, well, we're not going to innovate. We're not going to do anything else in order to modernize relational systems, even though a lot of companies out there, for a large part, still have to use relational systems, but of course want some of the modern benefits that we've seen from things like sharding and horizontal scalability and flexibility from NoSQL. And so some innovations have come throughout the last decade, and really the last 5 years pretty heavily around SQL. So again, kind of keying into the structured query languages. And before I mentioned that structured query language is a declarative language. So what happens underneath the hood is completely up to the implementer, right? So the implementing system that lets that happen. You're simply saying, oh, I want to create this, or I want to insert that, or I want to select this. And that's very important because as we started to get into being able to take the lessons that we learned from the NoSQL movement, relational databases started to incorporate things like semi-structured data, this ability to have more flexible data storage mechanisms and access and retrieval and manipulation, as I get into, by combining both relational and non-relational, what you could think of as semi-structured data. So this ability to still have your tables, but then be able to store JSON in there, and accomplishes this by keying into the structured query language, right? Being able to have functions or executable chunks of declarative code that you say, hey, go validate this JSON, and it validates it, and then it can put it into, say, a string field in the table. And then every operation where maybe I want to update the JSON inside of this table, it can run through a validation, say, yeah, this is valid JSON, or be able to sift through an array, or even be able to add constraints, right? Be able to mix some of the benefits of having relational databases with semi-structured data. But also that wasn't really the end of it, right? It's just getting started, where something that existed for a while in this whole idea of data warehousing was being able to store the data differently. So rather than on the left-hand side, we've got more row-based or tabular-based, right? Where you've got a table that may exist in a file or multiple files. Instead, we decided to incorporate column-based format or column-based storage into relational systems, where you could split up the columns and store them into an individual file or multiple files. And why is this important? Well, if we take, for instance, an aggregation query of something like average, where we're looking at the average of column 9 and we're wanting to see it from a particular table. Well, in a row-based system, what's going to happen is if you want to average that, you're going to scan the whole table on the left-hand side here. Take that box away now, not too distracting. But on the left-hand side, you're going to have to scan that whole table, right? And what's going to do is, theoretically, if every row were 200 bytes and you really just wanted to average column, well, you're having to look at about 200 gigs of disk IO, right? All that data on disk, in order to be at 1 billion records, in order to be able to have that aggregation. On the flip side, if you store things in a more columnar format, you're still getting the advantage of using the structured query language and relational systems, but you only have to look at that file or multiple files for column 9. And that can be significantly less if the column size is only 4 bytes. You're looking at 1 billion rows. That's only 4 gigs of disk IO. So immediately you get drastic performance improvements by simply changing the way that the data is stored and accessed, right? And still being able to use it or access it using the structured query language. And then that opens up a whole other can of worms, where now you can combine row-based and column-based information into a single unified query, right? Being able to cross-engine queries, so look at row-based data and column-based data, so that these applications that want to do operational tasks, but also want to be able to combine the benefits of maybe billions of records of historical data, you can do that all within split second, all under a second, without having to add things like indexes to your column-based information. Simply store it differently and be able to incorporate that. So you get this whole idea of real-time analytics through something called HTAP, or Hybrid Transactional Analytical Processing. Pretty long name. Just think of it as like operational analytics. And lastly, I want to mention this whole idea of distributed SQL, which is kind of a subset of something called NoSQL. And it takes the lessons learned specifically from NoSQL and being able to distribute data, SQL data, in these things called nodes, right? And that may be familiar if you're familiar with NoSQL. And you have a cluster of these nodes. And then each one of these nodes can be individually communicated with, right? So if you got an application, you can talk to node 1 or node 3, but you can retrieve all of your information and be able to do that because underneath the hood, we use these things called consensus algorithms that essentially will do node-to-node communication in a fully distributed manner, right? So it's a little bit more complex than that. But the idea is that like NoSQL, you get this ability of having to be able to scale up, right? This theoretically unlimited scalability. Right? And so you could scale up to handle your massive workloads in a relational manner. So you get all of the benefits of elasticity and scalability, but you don't have to worry about missing out on things like modern transactions and ACID compliance. Plus, as opposed to NoSQL, you can implement this in a way that you're used to, rather than a lot of the gobbledygook that comes with having to manage ACID transactions in a language for one NoSQL engine or another NoSQL engine. You can do it using SQL. And of course, you get the ability to have elasticity or kind of scale down so that then you get to very efficiently use the resources, right? So rather than having to buy all these machines up front, you can combine this with modern innovations such as the cloud, and then be able to use distributed SQL in this way in the cloud that allows you to not only have data that is massively scalable and elastic, but to be able to be very cost efficient as well. And with that, I would like to say thank you very much for joining me on this journey as we looked into just the modern innovations of databases in general and how we're still just learning lessons in this great data experiment. If you'd like, there's a short plug here, but if you'd like to know more, you can head out to mariadb.com/developers. Everything there is completely free, completely open source, and there's a lot of different types of developer content on being able to use a lot of the modern innovations I went over, such as JSON and column-based storage and distributed SQL. If you have a chance, go and check it out. It's all free, it's all open source. So thank you very much.